Hello. Can you hear me? Perfect. Okay. Dum dum dum. Okay. Should we start? Do you have any questions? Hello everyone. Okay. So I'll just do one thing today and we'll leave it at that. Okay. So what I want to do today is the Chinese remainder theorem. So let's just Alright, so let's begin. The Chinese remainder theorem. And it's centered around a simple problem. So here's a problem. We've so far in the previous class looked at trying to solve an equation of the form ax congruent to b mod m, right? These are the kind of equations that we try to solve, and we solve them by finding an inverse of a and multiplying a on both sides. A inverse, we wanted a inverse modulo m. If we can find a inverse modulo m and multiply it on both sides, we can find a value of x modulo m. The problem that will lead us to the Chinese remainder theorem is closely related. Here's the problem. Let's say you have a system. Let's say we have, suppose you have a system of congruences, right? So let's suppose you have x congruent to a1 mod m1, x congruent to a2 mod m2, x congruent to a3 mod m3, and so on, let's say up until n, right? So dot 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 x is also congruent to an mod n. So what are these equations? Sorry, mod m sub m. So what are these equations saying? So the first equation is saying that when x is divided by m1, it leaves a remainder of a1, right? That's what it's saying. Imad, I will answer your query at the end. Okay, so that's what it's saying. The second equation is saying that when x is divided by m2, it leaves a remainder of a2. So you have n such statements that when x is divided by m3, it leaves a remainder of a3. When x is divided by m sub n, it leaves a remainder of a sub n. So we want an x that satisfies all these properties. That's the main problem. But here's one important thing, and the condition is that m1 to mn are pairwise relatively prime. What does that mean? It means that the GCD of M1 and M2 is equals to 1. That M1 and M2 are relatively prime. It also means that the GCD of M2 and M3 is 1. That is, all of these take any two M's from this list and they are relatively prime. That is, they do not have the greatest common divisor that they have is 1. In other words, they don't have any common divisors, right? So they're relatively prime. And so I can encapsulate this condition by saying GCD of Mi, comma Mj is equals to 1 for 1 less than or equals to I less than j less than or equals to n, right? So if this statement helps encapsulate that idea that they are relatively prime. Okay, and so that's the problem. We have to find a value of x that satisfies all of this equation, that when you divide it by m1 it leaves a remainder of a1, when you divide it by m2 it leaves a remainder of a2, and you have to find such an x modulo all of these numbers, right? Okay, and so that takes us to the Chinese remainder theorem. And here's first, let's just try to solve that system of congruences, right? And so firstly, what the Chinese remainder theorem tells us, that in essence the Chinese remainder theorem tells us, the statement of the theorem is as follows. The statement says just that a unique solution to the above problem exists. Above problem exists. That's all the theorem says, that if you have a problem that's set up like that, that if the conditions are that these m's are relatively prime and x leaves the remainder of a1, a2, blah, 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 then a unique solution to this problem exists. And now we find that solution. So let's construct that solution as a proof. Okay, so let's consider first, consider k between 1 to n. So we're taking some k between 1 to n and we're constructing a number called mk by taking m. So first, actually hold on, before we do that, let's first make m as a product of m1, m2, dot, 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 mn. So we take all of these numbers m, which we were taking the modular arithmetic to with respect to in each of these equations, and we multiply them to give us the small m number over here. Okay, and so now consider, at this point we say consider k between 1 to n, and we create this number capital Mk, such that capital Mk is just m divided by mk. So for example, as an example, capital M1 will be m divided by m1, which is, since m is m1 to mn, m1 dot m2 dot 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 mn divided by m1, you can say that m1 cancels out and capital M1 will have m2 dot 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 mn. And so similarly, all of these mk's, this mk would have m1, m2, it will have m dot 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 mk minus 1, it won't have mk, it will have mk plus 1, and then dot 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 mn, right? So the important thing to notice here is that mk will be missing because it's cancelled out. Small mk has been cancelled out because it was divided by small mk, right? And so then capital Mk consists of all of these numbers. Now, At this point, I can state the following. I know the following fact, that since I have removed small mk, then I can state the following, that the GCD of capital Mk and small mk is equals to 1. This is because all of these numbers m1 to mn had no common divisors. This is something that we established from this fact, that they were relatively prime, so they had no common divisors. And so capital Mk and small m had small mk factor common. When you remove mk, so notice that this number has mk missing, so this number has small mk missing, which means the remaining numbers that are in here, m1, m2, m3, blah blah blah, have no common divisors with this small mk, and so these numbers are relatively prime. So in essence, what I'm trying to say is that m1 ... mn up until mn with mk missing is going to be relatively prime with small mk. Okay, so the GCD of these two numbers has to be 1, because all of these numbers were relatively prime with each other, which means they were relatively prime with this as well. And since we've removed small mk from this list, that means that they're going to be relatively prime. And since they're relatively prime, now this brings me to constructing the inverse. So we said recall, if I recall that if the GCD of a and m equals to 1, then there exists a unique inverse of a modulo m. So since we know that the GCD of capital Mk and small mk is equals to 1, then I can assert that there exists an inverse of mk modulo small mk, right? Because the GCD is 1, so I'm just applying this theorem. We're just applying this theorem to the above fact, right? Okay. Any questions up until this point? Or should I continue with the proof? All right. So at this point, we're ready to make these inverses. So let's construct these inverses. So since we know that an inverse exists, let's say yk is the inverse of capital Mk modulo small mk, right? Which means, in other words, I'm just saying that capital Mk multiplied by yk is going to be congruent to 1. That's what it means to have an inverse mod small mk, right? Now, here's the interesting thing. Let's I claim that I can now make my x that satisfies this equation. So let x be equals to a1 y1 capital M1 plus a2 y2 capital M2 plus a3 y3 capital M3, and you can see the pattern now, so I'm just going to extend this to an yn mn, and my claim is that this x satisfies the system of equations. What system of equations? The system of equations that we created here. So let's call this system, I'm going to call this system, let's say call this system 1. And so this particular x that I have, it will satisfy system of equations 1. And let's check how it will satisfy this system. So let's consider consider the equation. So let's pick any equation out of these 1 to n equations. Let's consider any equation, and so let's pick the kth equation, right? So consider the kth equation. What's the kth equation going to look like? The kth equation is just going to look like x is equals to congruent to ak mod mk, small mk, right? And I'm claiming that this x that I've just made, it will satisfy this equation. So let's check. So I'm taking, let's find x mod small mk, then that's just going to be this, I'm now talking about this x, okay? And so if I take small mk modulo small mk, then notice what will happen. So I will have all of these terms a1 y1 m1 plus a2 y2 m2 plus dot dot dot. Let's put an ak yk mk as over here as well, so that we know that we're referring to some term, and then up until an yn capital Mn. And I want to take modulo small mk of this entire equation, okay? Now notice that the small mk is going to appear, these are all capital MKs, right? So this is capital M1, capital M2, capital Mn, and this is capital Mk. Only this M will have the Mk term missing, right? The rest of these M1, so M1, M2, dot dot dot, Mn, excluding capital Mk, will be multiples of small mk, because they would look something like this. So m1 looks like m1, capital M1 has small m1 missing, but it has m2, it has all the other terms, it also has small mk dot 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 mn. So this one has mn, this one also has mk, this one also has mk. So mk will appear in all of these terms, which means mk, small mk, is a factor. Small mk is a factor of these m1s to mn, excluding कैपिटल mk. तो इस लिस्ट में से आप कैपिटल mk निकाल दें, बाकी सबका small mk will be a factor, right? So the small mk will be a factor of all of these other terms. Now, if it's a factor, of course, we know that if capital M1 to Mn are multiples, then of course the GCD, or sorry, the remainder when M1 is divided by Mk is definitely going to be equals to 0, because it's a multiple, right? In other words, we say that small mk will divide M1, small mk will divide M2, and so on, except capital MK. ठीक है? Any questions? Which essentially means that if I divide a1 y1 m1 by mk, small mk, the remainder has to be 0, because this term is a factor of small mk. So mk, small mk divides a1 y1 m1, sorry, capital M1, this is capital. Small mk divides a2 y2 m2, small mk divides a3y3, m3, and so on. You get the idea. You will get it in a moment. So just remember that we're trying to solve this system of equations, okay? And you will have the answer in a bit. So let's copy this and let's see what we get, okay? Oops, wanted to copy this. Control C, stick it down, okay. So consider this equation again. So mod mk, all of these, what I've essentially stated that this term, and all of these terms except this small ak, yk, mk, capital Mk, all of these will be 0 mod mk, because when you divide it by small mk, we've just established that they are all multiples of small mk. So this is 0, this is congruent to 0, and this is congruent to 0, which means x is equals to ak, yk, mk mod mk. And here's the congruent to. And here's the other fact. Notice that we established, we constructed mk. Let's copy this. Recall that this was something important that we did. So on the side here, I'm going to keep this fact, the fact that capital Mk and Yk are inverses of each other, right? So this little fact tells me that when you multiply these two numbers, then with respect to small mk, they are inverses of each other, which means this is just equals to 1, which means I have established that x is congruent to small ak mod mk. And this gives me the fact that x satisfies the system of equations that we had. So notice what I did. I started off with this problem with this system of equations. And we systematically constructed an x. So this is the x. If you're looking for the solution, then the answer to my equation is this, that this x is your solution. So this x will satisfy all of these equations simultaneously. It will satisfy this equation, it will leave a remainder of a1 when divided by m1, will leave a remainder of a2 when divided by m2, leave a remainder of a3 when divided by m3, and you can construct it by using these terms. So a1, a2, a3, an you already have, m1s. So the idea is that x is the solution. Oops. So the solution to this equation is x is equals to a1 y1 m1 plus a2 y2 capital M2 dot 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 an yn mn. And so a1, a2 up until an are known. m1, m2 dot 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 capital Mn can be found by small m divided by, that formula, small m divided by mk. This was the formula, mk equals to this formula. And yks are inverses of the particular capital Mk's modulo small mk. So you already have these, you find these terms, you find the capital M's and you find the Y's, and then you put them together in this way to construct this x, and you will have the solution to your system of equations. So does that answer your question, Kiblatan? Why are we doing this? We're doing this so that we have an x that satisfies all of these equations. Let me know if you have any questions with this solution. If you don't, we'll do an example. Perfect. Any questions? Manahil, Subhan, Imad? Okay, so if you don't have any questions, let's do a problem. Okay, so here's the problem. The problem is as follows. The remainder when x is divided by 2, sorry, divided by 3 is equal to 2. The remainder when x is divided by 5 is equal to 3, and the remainder when x is divided by 7 is equal to 2. Find x, right? So this is the problem, and the problem of course can be translated into the language of modular arithmetic, which is as follows. So this is a system of equations that we have to write down. So we're saying that when x is divided by 3, it's equals to 2, which means x is congruent to 2 modulo 3. When it's divided by 3, it leaves a remainder of 2. Similarly, x is congruent to 3 modulo 5, and x is congruent to 2 modulo 7, right? So these are the equations that I'm looking to satisfy, right? So I want a number that is that can satisfy all of these equations. Okay, all right, so here's the solution. So the solution of course is as follows. So this is x equals to a1 mod m1, x is equals to a2 mod m2, and x is congruent to a3 mod m3. And of course the solution, the answer is of course x is equals to a1 y1 m1 plus a2 y2 m2 plus a3 y3 m3. Now I have to find all of these terms. I have a1 is 3, a1 is 2, a2 is 3, a3 is 2, but I have to find these y1s and m1s, right? So the first thing that we do is to create let's just, this is an example, so let's just do it with blue. Okay, so here's the thing. Okay, so first off we will find small m, which is m1 times m2 times m3. We just need to multiply these together, which is 3 times 5 times 7, which is 15 times 7, 21, 21 times 5, 105. Okay, so this is small m1. Now we construct capital M1, which is 105 divided by small m1, which is 105 divided by 3, which is equals to 5 times 7, so 35, I think. Okay, small m, capital M2 is simply, let's just write it like 3.5.7, that was small m. So notice that I'm using the formula mk equals to small m divided by small mk, right? So that's the formula I'm using. So if this divided by small m2, which is 5 and 5 cancel, that's equals to 21, and capital M3, which is equals to 3.5.7 divided by 7, 7, we have 15, right? So capital M1 is 35, capital M2 is 21, and capital M3 is 15. So I have these terms now as well. So I have this, and I have this. Now all I need to find are the y1. So y1 is the inverse of capital M1 modulo small m1, right? So I want the inverse of capital M1. So I want the inverse of 35 yk is congruent to 1 mod, what was small m1? The small m1 was 3. Small m1 was 3. Okay, so I'm looking for the inverse. Okay, and you can find the inverse by using the method that we did in the last class. You can do it using, I don't know, the Bezout coefficients. I'm just going to write down, and so this is y1. I'm just going to claim that y1 is equals to 2, right? So y1 is equals to 2. So I'm claiming that I already know that when you multiply 35 times 2, that's congruent to 1 mod 3. And we can check this, of course. This is equals to 70. 70 mod 3 is, when you divide it by 3, you will divide it by, the last multiple that you get is 69 plus 1. So it's basically 13 times 3 blah blah blah, or 23 times 3 plus 1. So 1 is the remainder. This is not systematic. I'm just proving that this is the inverse. This is the right inverse, right? So 70, when you divide 70 by 3, it will leave a remainder of 1. Okay, so I'm claiming that I know that y1 is equals to 2, and you can find the base till m1. Capital M2 was 21. So 21 dot y2 is going to be equals to 21 times 1, which is equals to 21. And now if I divide 21 by mod m2, which is basically 21 mod 5, then I know that this has to be, when you divide by 5, it's basically 20 is the last multiple plus 1. So that's your remainder. So I know that this is also, I've verified that this is the right inverse. And similarly, y3 is equals to 1 as well. So the idea is, I am claiming that m1, so y1, let's just write these down. So I have 35, 21 and 15. m1 equals to 35, m2 is equals to 21, and m3 is equals to 15. y1, y2, y3 that I've found are equals to 2, 1 and 1. And the idea is, I'm claiming that m1, y1 is congruent to 1, will leave a remainder of 1 modulo m1, which is, m1 for us is 3. m2, y2 will leave a remainder of 1 mod small m2, and m3, y3 will leave a remainder of 1 mod m3. Okay, so these are the values that I've found. And so now I can go ahead and I can construct x. So x is equals to, so I have a1. Let's look at my a1s. What were the a1s? A2 and y1. Let's just write those as well. So they were 2, 3, 2. So a1, a2 and a3, they were 2, 3 and 2. And so now we just write down the terms. So the first term is 2.2.35 plus we have 3.21.1 plus 2.15.1. And so when you write these all together, these are x is equals to, when you add them up, this is going to be equals to 233. Now the important thing over here is that this 233, the solution, when you combine all of these, one thing that I forgot to write is there exists a solution of this mod. This solution is basically, when you've combined all of these terms, this solution exists, a unique solution exists in mod m, where m is of course m1 ... mn. That is, this number that you found is not just an simple number. This number, the solution is unique in modulo small m, and this small m is of course, so this small m is simply just 233 mod, this was the multiplication of all of these small m, so this is mod 105. So when you find the remainder of 233 when divided by 105, that's just equals to, so if I divide 233 by 105, I will get something like 105 times 2, which is 210, plus I will be left with a remainder of 23. So this is remainder. So my solution is 23 mod 105, and that's my solution. So let me just add that little fact over here, that this solution is going to be x over where is it, where did I, yes, right here. This solution, by the way, this is in mod m. Okay, and that's it. That's how you use the Chinese remainder theorem to find the solution to the system of equations. And just to verify, if you want to verify it, then to verify, you can check that 23, this 23 that you have, you can check 23 should be congruent to, it should satisfy all of these equations that you have. So it should satisfy 2 mod 3, it should satisfy 3 mod 5, and it should satisfy 2 mod 7. So let's just verify that and right now. So if I divide 23 by 3, the multiple is 21 plus a remainder of 2. So that's your remainder. Similarly, if I divide it by 5, then it's 20 plus a remainder of 3. Similarly, if I divide it by 7, then it's 21 plus 2. So that's your remainder. So 2, 3, 2, which is the same as 2, 3, 2 over here. Okay. So this 23 satisfies all of this equation. Okay. And that's it. That's your solution. So x is equals to congruent to 23 mod 105. Any questions? Nope, all clear, great. So that's all the number theory that I'm going to do with you. Of course, this is just a introduction to number theory, and I haven't even gone through the entire chapter that we had, chapter 4. Some of the things that I've left out, you can go through them yourself. They're quite interesting topics. There's something about the Fermat's theorem and pseudo primes and whatnot. There's some application of hashing as well. So you can check these out yourself. I'm going to end number theory here, and we'll start doing something else from the next lecture. Okay, I'm going to end this early today. Imad asked a question which I'll just answer. Imad, if you're listening, in the project proposal, you don't just have to state the topic, you have to give me a little bit of information about what you are going to do with the topic. Just a little brief overview of what ideas and what things you're going to discuss in your report. Okay, just a brief, in a couple of sentences, just explain to me what you're going to do. Okay, that's all. Okay, so that's it. If you have any questions, I'll hang around for a couple of minutes, otherwise we can just end this. Okay. Have a good day, everyone.